Hello everyone, my name is Jad Wahab and this presentation is about scaling Bitcoin for global adoption. Now I know there have been many presentations in the past with a similar title, but this presentation has a few things that have never been spoken about publicly yet. So the proper way to scale the Bitcoin blockchain for global adoption is to basically use the Lightning Network. No, it's not. No, it's not. So what I'm actually going to be talking about is SPV. So I'm going to start off giving an overview on Bitcoin scaling. Then I'm going to discuss simple payment verification, SPV, what it is, why it's important, and how exactly it can be used. And then I'm going to go through an end-to-end SPV flow, covering existing tools and highlighting missing tools and tools that need more work. So this is the Bitcoin network. It's represented by a Mandala network, which consists of two main components, the highly connected center of nodes being the first, and the second, the rest of the users on the outside connecting in as well as to each other peer-to-peer. Now, in order for us to scale Bitcoin, it's not enough to only scale the nodes or the miners, which are essentially the same thing. We need to also scale the users. So work on scaling Bitcoin, the user side pretty much started when we had a few mainnet stress tests and services like Money Button and others started falling over. And at that time, everyone was just running their own node like it was a normal thing. And but then everyone realized that we can't keep this up and we need to do things properly with SPV because users don't need to run a node and they shouldn't have to validate every single transaction on the planet. Instead of just caring about their own, they should just be worried about their own transactions and leave the rest up to the nodes. So this is another cliche Satoshi quote, but it's just to remind people that there really isn't anything new here. You know, in the early days, even Satoshi in 2010 said that the current system where every user is a network node is not the intended configuration for large scale. And that would be like, you know, every Usenet user running their own NNTP server, and the design supports letting users just be users. So, you know, we're not just doing things the way they were originally designed as some sort of PR stunt. We've studied other blockchains, other solutions. We've come to the conclusion that the original Bitcoin design is the best solution. And it still blows my mind that Bitcoin's original design is the best one out there, despite being the first and not just because it was the first, as some people imply. So simple payment verification, SPV, it's basically section 8 of the white paper. Clearly states that it's possible to verify payments without running a full network node, and we'll see why in the next few slides. And the user only needs to keep, you know, the header chain, which is the copy of the block headers of the longest proof of work chain. And before I explain SPV and how it really works, does anyone want to guess how many proper SPV solutions there are after 12 years of Bitcoin's existence? Zero. There's zero proper SPV solutions, or else I wouldn't be sat here giving this presentation or writing the tooling for it, would I? So this is how the Bitcoin blockchain works. Basically, the word blockchain is a bit misleading. It should more accurately be called the block header chain, because the way it works is the Bitcoin block headers are chained together, and each block header is only 80 bytes that include the version, the previous block hash, which it builds upon, the Merkle root of the transactions, the timestamp, the difficulty target, and the nonce. So each header is only 80 bytes, regardless of how big the block is or how many transactions there are in the block. All transactions get put in a Merkle tree, and only the Merkle root is in the block header. And basically, there's a reason why there are Merkle trees in Bitcoin. As you can see in my extremely naive drawing, you can keep adding more transactions into the Merkle tree, and that won't affect the size of the headers. basically all you need to do is just keep a copy of the headers, and the nodes take care of the rest of the transactions. All you need to care about is having the header chain, and if you've got a transaction, as you can see here in yellow, all you need is the Merkle path in light blue to prove that the transaction actually existed in the block, and that's all you need to cryptographically prove that. So you don't need the whole block, all you need is the header chain. And if you had a limited size block of 1 megabyte, like on BTC, there would be no reason to have a Merkle tree. Basically, all you would do is just hash the transactions all together and put that in the block header. You're just adding unnecessary complexity by having a Merkle tree, since everyone on BTC runs a full node and there's no differentiation between nodes and users. That's why no one really uses SPV on BTC. So this would just, adding a Merkle tree is just adding extra unnecessary complexity. And technically, so I don't get called out on this, what you would do is you would actually hash the Coinbase separately from the rest of transactions because of the extra nonce. But anyway, you get my point. So these are a couple of diagrams from my previous presentation I gave about Mapi. And for those of you who haven't seen it, Mapi is pretty much just an interface into nodes or miners. But if you want to understand Mapi in more detail, you should check out my previous presentation. But pretty much in these diagrams, I compare a legacy to peer-to-peer payments. And I just wanted to clarify a few things. So the way legacy payments used to work on Bitcoin is the sender would send transaction to the network, and then the receiver would scan all the transactions on the network and filter out for the transaction that they're interested in. And I just wanted to say that it's not technically not unscalable, it's just over expensive, because you could have someone send you a payment to the network and have a service provider scan the network and send you the transaction that you're interested in. So it's still doable, but it's just over expensive. It's like buying a private jet to send a letter from London to New York. No one's going to do that, but no one's actually stopping you from doing that if you had the money and you really want to do that. So also to clarify one more thing on the peer-to-peer payments diagram. So there's actually one thing missing. So it's having the receiver broadcast the transaction is one step further, but it's still missing something. So the way peer-to-peer payments work is you hand the receiver the transaction, and the same way you would hand a check to someone, they would cash it at the bank. You hand the transaction to the receiver, and they would settle that on the blockchain. So the difference here that was missing in the previous presentation is that the merchant or the receiver would validate the transaction, and then if it's invalid, they would reject it. If not, they would settle that on the blockchain and broadcast it to the nodes. So how does transaction validation work? First of all, you need to make sure that the sum of the input Satoshis is greater than or equal to the sum of the output Satoshis, or else you'd be essentially creating money out of thin air. You also need to validate that the unlocking script, previously known as the script sig, in the input can unlock the locking script, previously known as the script pub key, in the output UTXO being spent. So, and basically this is an example transaction. And with the input here, as you can see, it's got transaction ID of the UTXO, the index, and the unlocking script and the sequence number. But if you notice something, if you look at the output that it's spending, there are a couple of things missing. There are two main fields missing. So there's the value Satoshis that's missing and the locking script that's missing. And in order to validate the transaction, you need that data from somewhere because it's not in the payment transaction itself. And we'll cover that in more detail later on. But basically, once you validate the transaction, you need to send it to a node in order to check if the UTXOs are unspent, meaning that there's no double spend involved. And basically, we trust the competitive nature of the miners and the nodes, and that's why this is secure, because you can't get a double spend into the blockchain, or else your block is going to get orphaned by the rest of the nodes. So I know people are thinking this because it's a common question that people have about the situation. What's the point? So you may not be convinced and maybe thinking, why should the merchant receiver even validate the transaction? The node or the miner will do it anyway. So what's the point? So it's not. So it's not because of any theoretical reasons. There are real practical implications for not validating the transaction before broadcasting it. So first of all, for example, how would you check how much fees a transaction is paying? So let's say a sender sends you a transaction not paying enough fees that you would like, and then you send it to the miners, and then it gets accepted by the network. It's too late. You can't update it. There's no replace by fee. So that's a huge drawback of not validating the transaction yourself. Another one is state channels. So how would you validate an interim state of the state channel before broadcasting it to the network? So you need to validate the transaction yourself. Also, if you have multiple inputs, are you going to wait until all of the inputs are signed and received before validating the transaction? I mean, we're not going to have only transactions with one pay the public key hash input and two pay the public key hash outputs, one for change, forever. Things are going to get much more complex. Multi-sig, spending multi-sig outputs as well. You want to validate that in interim states without having all of the signatures yet. Also spending complex scripts, which potentially could be very expensive in the future. So you want to know that before broadcasting and potentially reject that transaction from a sender. Also, if you're just sending invalid transactions to the network, nodes could get banned. Obviously, that's something you don't want. Error messages is a big one as well. So the node doesn't return the best error messages always. And if you've been programming Bitcoin, you probably know that already. For example, missing inputs, it's not the best error example. So if you validate a transaction yourself, you could know exactly what's wrong. And basically, yeah, these are just a few practical implications. I'm sure you guys can think of a lot more, but validating transactions before accepting them actually relates a bit to the up push transaction technique that a lot of people in the industry are using now. So I'd like to just quickly go over that a little bit. But before I explain up push transaction, let's just go through quickly how spending a UTXO works in Bitcoin. So you have a transaction here, a UTXO, pay the public key hash UTXO, and you want to spend that. And then another transaction, basically you need to include a signature and a public key in the locking script. And what the signature is signing is this sig hash pre-image, which includes these fields, and a lot of them, for example, the version, the unlock time, a lot of them are outside of the script itself. So the way up push transaction works is, usually nothing should be able to access any data outside of the script, but up checksig can, and this is what up push transaction takes advantage of. And that's why we called it a Ying's hack back at nChain before it was called up push transaction, because it takes advantage of something that's in a hacky way, basically, that wasn't intended. That wasn't its intended purpose. So the way up push transaction works is basically you push the sig hash pre-image in the unlocking script with a random private key, and then in the locking script you ECDSA sign that sig hash pre-image and then use op checksig. If the checksig passes, then you know that you have the same sig hash pre-image as the current transaction and can use values in there like the previous transaction script or the unlock time, etc. So in the locking script, you would include extra logic. You could force the output script to be a specific output, and people are using that to force an output of a transaction, spending a specific input to be exactly the same as the previous output script of the input, basically carrying forward the script, sort of like a Ethereum smart contract. You could also force the output value to be a specific amount. You could force the unlock time to be a specific amount, but there's, for example, with op CLTV, the reason why we got rid of it is there's no real need for it. There's cheaper and better ways to do it. And when validating a transaction with SPV, you can check the outputs and whatever logic that you want and reject if the transaction doesn't follow the specific logic rules, the same way you would do with a push transaction. But the difference is these rules don't need to be in the transaction script and enforced, enforced by the miners. Anyway, that's enough about All Push transaction for now. I don't want to take anything away from Xiaowei's presentation tomorrow. I really like his work, and I'm sure his presentation will be great. What I want people to take away from this is to think carefully about what their solution is trying to really achieve and not just jump to conclusions. There are no silver bullets, and All Push transaction is not cheap. So we've gone through why scaling Bitcoin with SPV is important. Now let's talk about how to go about doing that exactly. So this is a diagram of the SPV flow end-to-end, and it's pretty similar to Mike Hearn or BitPay's payment protocol setup, but more advanced and with less complexity involved. So I know this looks a bit overwhelming at first glance, so I'm gonna go through it step by step, don't worry. And before going through the flow diagram, I just wanted to give you a taste of how the UX looks like so that it would be easier to understand the flow diagram. So this is an example video of a Handcash wallet buying something at a store using AnyPay. So what they would do is take their Handcash wallet, scan the QR code of a specific item that they want to purchase, which is essentially the purchase order. And then their wallet would basically get the information for that transaction. And then you would swipe to accept the transaction, essentially signing and sending the payment to the merchant. So I'm going to go through the diagram and highlight specific parts that need work and more discussion, and I'll discuss them afterwards separately in different slides. So in the beginning, the customer wants to buy something from the merchant. They create the basket of goods, which is essentially the purchase order, as you saw in the Handcash example. And the merchant would create the invoice with X amount of Satoshis and then display the invoice as a QR code. So let me just break that down a little bit. So this constitutes the payment protocol initiation. The first part is essentially service discovery. So you need to discover the merchant, and some solutions such as Paymail do that service discovery, but something missing with Paymail is invoice creation, and we'll discuss that a bit more in the later slides. So basically the way this works with the payment protocol that Handcash and AnyPay use is once the merchant creates the invoice, they basically create an invoice ID for that item locally in on their servers, and then they display either a link with this URI, or they encode that into a QR code, which the wallet scans, and that's where they obtain the payment protocol URL, and that's how they know where to fetch the payment request with the invoice ID. So after that, the customer's wallet fetches the payment request, and then from the merchant at this endpoint, and then the merchant would get a policy quote from a node using Mappy. And what a policy quote is essentially it's just an extension to the fee quote with other minor policies such as the ancestor limit and stuff like that, which is being added to Mappy. And once the merchant gets the policy quote response, they can work out the payment request arguments, for example, the outputs that they want to receive, the payments to, the fees, etc. So this is how a payment request looks currently. As you can notice, the fees are not included, which we'll discuss in the next slides as well. And then the merchant would respond to the customer's wallet with this payment request. At that point, the customer needs to authorize the payment, which is where you saw the user swipe to accept the payment, click OK, and then that's where the payment is sent to the merchant. So one thing missing from the current implementation is all of the metadata or extra data needed to validate the transaction, which we're denoting as the SPV envelope. So this consists of the input transactions, the Merkle proofs, and we'll explain that in the next slides as well. And that's also missing from the current implementation. And then once the merchant receives the payment transaction, they also need to validate it. And at the moment, it's not being validated using the right approaches. So we'll discuss that later as well. Once the merchant validates the payment transaction, if there's an error, it would immediately reject it, and then that ends it right there. Or they would then broadcast a transaction, so post it to a MAPI endpoint, including their callback URL, so that they can immediately be notified for any double spend notifications, double spend attempts, and afterwards, when the transaction is mined into a block, they can get the Merkle proof for it. So if they get a success response from the miner, they would then respond to the customer with a payment acknowledgement. And then afterwards, this is something that doesn't exist yet, but obviously the customer needs the Merkle proof of the transaction as well, because likely they will have a change output and they will need the Merkle proof for that as well. So there needs to be an extension for the MAPI in order for someone who's not submitting the transaction to get the Merkle proof of a specific transaction. Maybe they can resubmit or query transaction, but there needs to be an addition to MAPI for them to also get a Merkle proof. And one more thing to mention is how would the merchant or the customer discover the right MAPI endpoints, and we'll discuss that in the next slides as well. So the first thing I wanted to discuss is invoice creation. So it's currently missing with Paymail. With Paymail right now, if you want to send money to someone's Paymail address, for example, jad@moneybutton.com, you just send money to that address, you set the amount, it's not linked to any invoice or anything. And that was basically to mirror existing Bitcoin user experience where you send money to someone's address unsolicited, which is a really rare case. You're never going to be paying for someone unsolicited without, them having an invoice or anything, paying them and them requesting the payment. So this, I would say, in the future, it's gonna get even more rare, especially when all these new tools start being used more often. So similar to the payment request, we have a payment capability, which is the payment destination, and similar to the payment in the payment protocol, we have the P2P transactions Paymail capability. And the difference here is it's not linked to any invoice or anything. All you do is you request payment destination for a specific amount of Satoshis, you get a reference, and then you quote that reference when you're submitting the transaction. So it's not as good as a payment request or the payment protocol, which people call BIP 270. But anyway, it needs some work. So the second thing I wanted to discuss is the fees in the payment request, which are currently don't exist. So we need to extend the payment request in the payment protocol spec to include the amount of fees. So right now the merchant or the receiver gets the fees from MAPI, and they get the fees from different miners, and they need to decide which fee that they would set for the payment for them to accept that payment. So we need some work on this, and I'm sure this is something that a lot of people, a lot of wallets and stuff in the space will definitely benefit from. So we need to standardize this across different wallets so that we can get proper interoperability. The third thing I want to discuss is the SPV envelope. And this is in order to send the right data in order for the receiver to validate the transaction properly. So some wallets get the previous transaction data from an external service like What's on Chain, but that's not the best solution. It's just a hack at best. And the sender should send you all the information you need to validate the transaction. So what an SPV envelope is essentially it's a data structure encapsulating this information, this metadata that you need to validate the transaction, basically the payment transaction itself, or could be multiple transactions, the transactions that correspond to each input, as well as their Merkle proofs. And the sender will basically already have much of that information because they need the previous transaction info when signing the input. And there's currently a TSC work in progress getting started. So if this affects you or your company, please get involved and actively work on getting the right standard across different wallets. And the fourth thing which relates to that is validating the payment transaction. So I conveniently stole this great diagram from my colleague Jack. Basically shows the elements that I just discussed: the payment transaction, the input transactions, the Merkle proofs. And then, so once handed the payment transaction with the SPV envelope, you can go through the following steps to validate the transaction. For each input, you need to verify the Merkle proof, and there's an asterisk there because you need to validate the Merkle proof across the longest chain. So you need a headers client to essentially find the longest, most proof of work chain. And we have an internal headers client that will be released soon. And then second of all, you need to validate the unlocking script and check the fees paid or any other rules or logic similar to the push transaction technique. And then finally, you accept and broadcast the transaction to a node. The fifth thing I wanted to highlight is the Merkle proofs. So at the moment, the Merkle proofs have been standardized with the TSC, and it's in public review stages, so it should be finalized very soon. And MAPI version 1.3.0 uses the latest Merkle proof standard, as well as Bitcoin SV node version 108. And the last thing I wanted to highlight is MAPI. So how would you write code to discover MAPI endpoints dynamically? I know most of the MAPI client libraries right now hard code a lot of the node details into the code, which is not great. The Bitcoin design supports nodes joining and leaving dynamically. So why shouldn't our code? So some steps have been taken already to solve this. Bitcoin peer-to-peer messages have been extended in order for them to return the Coinbase transaction as well as the Merkle proof, along with new block headers. And once you have a headers client, basically you can extract the miner ID data from the Coinbase transactions of each block, and then you can find the data of the specific miners. Right now, it's just Tal, Mempool, and Mattercloud that are doing that, but as the blockchain scales and grows, I'm sure it's not going to be them three. So miner ID is going to be crucial for that, not to mention all of the other reasons why miner ID is important for scaling for miners directly. So once all of these 6 actions have been completed, we should have a fully complete SPV solution, taking us one step further towards scaling Bitcoin for global adoption. Now, myself, along with a bunch of others, including some at nChain, Tal, and Tonic Power, are building a lot of these foundational tools and building blocks open source in Golang. So for more information, go to gobitcoinsv.com. You'll find a collection of a lot of Golang Bitcoin repositories. And we've been also building extensive Bitcoin libraries under the GitHub libsv that started off based on Ryan and Muddy Button's JavaScript library. And then we just went for a ground up approach, removing all legacy BTC, BCH baggage. So it's just purely Bitcoin now. Right. If you found this presentation interesting and relevant to what you're currently working on, please reach out and get involved so that we can design the right standards for interoperability without missing anything or anyone. So you can reach out to me using any of the following methods. The sooner we can sort out scaling the Bitcoin users aspect, the better for everyone, and the faster we can move on to other things. Thank you.